Good afternoon, everyone. This is Jonathan Nicholson with ISP Supplies, and would like to thank everyone joining us today for the KP Performance Maximizing ROI and Best Practices with High Performance Antennas webinar. With us today, we have Mike Hoprich and Justin Pollock with KP Performance. Today, we will cover how to choose and install the right antenna, tower deployment strategies, channel planning, and some new upcoming antennas as well. We have a lot to cover today. We will also be recording and posting this webinar for anyone who may have missed it or would like to rewatch it. Please submit your questions and we will get them all answered after the presentation, time permitting. I will now hand it over to Justin and Mike. Gentlemen, the floor is yours.
Thanks,
Awesome.
Jonathan.
Thanks, John. All right, just waiting to get the screen. Perfect. So hopefully you see the KP Performance slide up and not the note slide. But yeah, today we're just gonna be talking about some very near topics to me is maximizing your return on investment for an antenna. Why should you pay more for an antenna when it looks on the spec sheet that it looks like the exact same antenna? There are subtle differences that are going to be seen once you deploy it in the field. And also we'll discuss briefly on some best practices for your point-to-point or point-to-multipoint antennas. So here's me. I'm just gonna change this over to a pointer. So that's me, Justin. So I've been with KP for a number of years now, and I also overlook the radio waves technical side. But I do everything antennas, all the way from parabolics to sectors to flat panels to Yagis. And we're part of the Infinite umbrella, and these are the number of companies under the umbrella right now. You're probably very familiar with Elcom, Pasternak, Fairview, Radio Waves, and Polyphaser and Transector. So here's our agenda, but let's just get right into it. So we're going to talk about antenna properties briefly here. I've been drilling this for a number of years now, but it's always good to back and revisit. So an antenna, many different properties to describe it. We're used to mostly just antenna type, the operating frequency and gain, and beam width. Those are kind of the main drivers for how we choose an antenna. But we also have to consider all the other parameters, such as how does the beam look versus frequency? Does it squint or point to one direction versus the other? Does it have a little bit of down tilt in it, electrical down tilt built into it? What's the front to back ratio? How do you define all these parameters? Their definition is going to change how they're spec'd on a specification sheet. So gain is one of the most important, and really it's what we see in the field. It's an absolute measure of the antenna's focusing of power. And gain is always relative to something. We have to define it. It's in a dB scale, and dB is always a relative quantity. So what we do is we define it relative to isotropic. That's why we have dBi. The I stands for isotropic. And isotropic means that let's say you have a point source or some type of antenna that can radiate equally in all directions. So it has said to have 0 dBi. But then what happens when we start focusing? Well, when you start focusing, you end up increasing a quantity called directivity. I'm surprised this, okay, there we go. Directivity. Directivity is essentially just gain without any loss. So gain without efficiency loss, material losses, cable losses, whatever it is. But directivity is just the amount of focusing an antenna does. So a horn, let's say, can have 10 dB directivity because it focuses everything forward. But once you start taking into account loss, let's say your antenna is only efficient by 50%. That could be from a poor VSWR or high material losses. You know, the RF energy gets stuck in the antenna, starts getting dissipated through heat. And if you have a 50% efficiency, that means 3 dB loss. So that means your directivity goes from 10 to 7. And this is what we see in the field. Actually, if I'm going to go and set up a link, you'll actually see the 7 dBi gain in your link budget. Now, to measure gain, you got to use a NIST calibrated standard gain horn, but there are other ways to measure gain that are not as accurate, but this is kind of the most accurate way. Some vendors will actually report a quantity called directive gain, and that's really directivity, and it's a little bit of a cheat in order to say you have a high gain, but really you have a high directivity, but you can have a poor efficiency antenna. So that's why when you look at the spec sheet, you can compare two of them. They say both 10 dBi gain. Just be a little bit wary of how they're defining that gain. It could also be an average gain or a typical gain, not a minimum gain. And typically gain doesn't stay one value across the band. It usually drops with frequency because the beam width ends up spreading in the elevation plane. But in any case, the definition is very important, and we just have some back of the hand calculations right here. So front to back is another very important parameter. Front to back is going to tell us how we can reuse frequencies. How far the antennas need to be spaced apart, or do they need to be on separate channels completely in order to make sure they don't interfere with each other. Now, front to back is often just defined as the radiation pointing backwards at 180 degrees. But this is not a really useful parameter because that only tells us that if you have an antenna right at 180 degrees and you're not trying to serve anyone between, let's say, -50, -150, and +150 with another sector back to back here, really it doesn't tell you anything about how much interference is going to happen in outside of that 180 degree point. So the better definition here is actually define it over an arc in red here, and then take the maximum value. And you can see that the front to back is a little bit more realistic. It's -33 dB instead of the -40. And this is actually what you care about when you're trying to reuse, let's say, one frequency between a sector pointing north and a sector pointing south. You want to make sure that in this whole arc here, we're using the sector, maybe it's a 60-degree sector, you're not going to see that interference in the backwards direction. Cross polarization is very similar. So cross polarization, the definition here is we radiate from the antenna the polarization you desire, your co-polarized or desired polarization. That's the green here. So let's say you excited +45 port and you want to radiate +45, so that's the green. Now the cross polarized waves that are exiting the antenna, these are the ones in red, and these would be -45 because you excited +45 polarization doesn't mean you want to excite -45. So you can see here that these are the polarization you don't want. You don't want to receive this because if this is on the same level as the green, you're going to have issues distinguishing between the MIMO chains, or at least the radio will. So it's not going to be able to distinguish between bits of information on the green curve and then versus bits of information on another chain, which has its own green curve, but it's the opposite polarization. So it's all about correlation. How do you uncorrelate these two signals? And so the proper definition here is we use cross pol. You can use this definition here at -32 dB right at bore site, but really we care about cross pol over the entire range of that sector is being used. So this is a 65-degree sector. So we look at the 3 dB beam width and the max cross pol level, and that's this value right here, -18 dB. And this is actually a respectable cross pol level. I've seen cross pols anywhere down to 10 to 5 dB, and you still get decent MIMO performance. So even though that this definition greatly reduces the cross pol level on the spec sheet, it's more accurate. And this is actually a useful parameter to you. Now, slant polarization, I put together these slides because we went and released our ProLine sectors, and a lot of them are slant polarization. We have released a few that are H&V now, but people are wondering, well, can I use a slant polarized sector antenna, AP antenna, with a CPE that's horizontal or slant, or horizontal polarized, horizontal vertical? And the answer is yes, you can. There's going to be a small dip in gain. The theoretical maximum that you would see between horizontal and vertical and 45 slant is 3 dB, but you're not going to see that in the field because once things start propagating away, the polarization starts kind of rotating. Also, it doesn't leave the antenna perfectly -45, +45. It's some small angle between that. So what ends up happening is on your receive side, you're going to see anywhere from maybe a half a dB to a 1 dB drop, and same on the transmit side. So just due to a polarization mismatch between the CPE and the AP antenna. So it's not game changing, and a lot of technologies can actually remove this polarization mismatch in the receiver side after they do all the signal processing on both of the MIMO chains. So why do we do this though? Is because it actually makes life a lot easier. First, on the antenna side, that you have symmetric patterns. So that means you're not going to see large chain imbalances, or you shouldn't, between the two chains. When you have H and V polarization, the H ends up being a lot broader beam width and fatter patterns pretty much than the vertical. Vertical is usually very highly focused and broader, and the horizontal is a little bit broader. So that leaves chain imbalances, especially at large angles, maybe near the edges of your sector. So that causes issues on the radio side because it's going to try to lock onto the strongest signal, and then the weaker signal, the chain is going to end up having issues being close to that receiver noise floor. So that's kind of one of the reasons why in the carrier world and then also in the LTE world that they went with this 45 plus minus 45 slant, because it's just much more easy to design for. Also, it has better multipathing characteristics. Now, here's just some basic principles of a sector antenna. So sector antenna is just a bunch of patches or slots or whatever it is. Antenna elements is the basic element here that's repeated in the vertical direction. And by repeating in the vertical direction, you narrow your elevation beam width and you increase your gain. So every time the beam width halves, your gain increase roughly 3 dB. It's not a linear increase because, or one-to-one increase, because at the same time your efficiencies do drop because you have some traces, wires connecting everything together, and as these wires get longer, you get more loss in those wires. So most antenna elements around the or antenna sectors are around 8 antenna elements. You can see here that the beam width here is 7 to 6.6 for this, but we have some that are 10 and 12 elements in order to get better elevation side lobe controls, but still have the same beam width. Plus our 90-degree sectors, some of them are up to 16 elements. You can see here with a 4.1 degree elevation beam width, and the reason for that is so you can have higher gain, especially for a 90-degree sector. It spreads it on the azimuth, so you want to narrow the elevation to have that high gain. Now, what is the difference between a sector and a horn antenna? Well, as I kind of mentioned, a sector is just a bunch of elements vertically stacked here. So sectors end up being long and typically rectangular, whereas a horn is circular and elliptical. And the benefit of having that circle and elliptical shape is that you end up having equal azimuth and elevation beam widths, which is great for filling in nulls, irregular terrain. The downside is the gain does drop. So for an antenna that has equal azimuth beam width to a sector, the sector will always have higher gain because the elevation beam width is narrower than the horns. So you end up having this big drop in gain when you go to a horn. But there's still a number of different benefits to having a horn versus a sector, or a sector versus a horn. Typically what I've been saying is that sectors are great for your macro deployment, rural, far away, where a horn is good for urban, suburban, where you want to put maybe multiple horns or AP antennas fairly close to each other to serve a high density area, or a select number of clients with high data rates. So here we're just comparing quickly a sector versus a symmetric horn. One thing I kind of forgot to notice or to mention here is that the beam width of horns is defined with respect to a 6 dB roll-off, where the beam width of a sector is defined to a 3 dB roll-off. So if you open up a data sheet for horn, it says it's a 40-degree horn, but that's with respect to its 6 dB roll-off. So that means within that 40-degree beam width, the pattern rolls off 6 dB near the edge. So if it's a 16 dBi horn, that means right at the edge of here at the plus minus 22.5 or plus minus 20, the gain rolls off 6 dB. So that means the gain on the edge is only 10. Whereas as a sector antenna, it's a sector antenna, it's rated for 45-degree beam width. That's with respect to 3 dB beam width. So that means if sector antenna here is 20 dBi gain, at the edge of its sector, the gain is only 17.5, which is, it's not that much of a drop off. We're talking about 1/2 the power versus 1/4 the power dropping off. So that's why when we do comparisons between sectors and horns, we have to make sure we're comparing apples to apples as much as we can, and we compare a 45-degree sector antenna, not compared to a 40-degree horn, because you can see that beam width is much, much more narrow. You actually have to compare it to a 60-degree horn. And when we do this comparison, you could see here, first of all, let's just look at raw patterns. The 60-degree horn and the 45-degree sector have very similar patterns. And in fact, the 45-degree sector, even though it has almost equal beam widths to the horn, it has much sharper side lobes here, doing much better. And it's also, very similar coverage rate, at least in the azimuth plane, as compared to that horn. But once you go plot everything in terms of linear gain, so that this plot here is actually plotted with respect to the maximum gain of the antenna. You can see here that the sector in red is going to do much better, higher gain over your intended coverage area than both of these horns. And we can see here that, yeah, the side lobes are a little bit higher here for our sector as opposed to both horns, but the front to back is almost equivalent. So that's kind of just some of the comparisons we see with sectors versus horns. Once you get on the ground, what does this mean? Well, like I said, the sector 20.5 dB sector versus let me just go back to the gain, a 13 dBi horn versus a 16 dBi horn, you're going to get out much farther. So these are ideal for your urban areas, or sorry, rural areas, the sector antenna. Now, an asymmetric horn, we've seen these for the last 8 months or so. These are, you know, a new antenna type that's come out, and essentially they're just a sector. Their goal is to narrow the elevation beam width as much as you can, but still have the same azimuth beam width, azimuth beam width and azimuth side lobe patterns. But what ends up happening is this you know, elongating of the horn ends up you know, ends up reducing the pattern quality or reducing the side lobe levels. I wouldn't say reduce, actually increasing the side lobe levels of the azimuth plane. So it's very similar to what a sector has, but by itself. So my kind of takeaway from this is these asymmetric horns, they end up being just sector antennas, but they end up being bigger too. They're longer. And they also end up not having the same amount of gain as a sector antenna. And that's because they can't narrow the elevation beam width enough to meet the same gain. And I mean, the horn would have to be 2 or 3 times as big to get to the same elevation beam width as what they are currently. So that's the comparison here between a sector and asymmetric horn. It's a new neat technology, but you're essentially just redesigning a horn or a sector. Now here is the comparison with 60 degree. I'm just going to skip this. Very similar talk. You can comment or review this by yourself. But a 65 degree sector is very similar to the 60 degree and 90 degree asymmetric horn. And here's just the difference of the coverage area. So very similar coverage, but the extra gain of the sector kind of gets you out just a little bit further, and you can pick up a few more clients and help get your return on your investment a little sooner. Now, we're going to pivot off and we're going to talk about some new products with KP. So here's some new products that we're working to get these on the website. These are cables with boots. So from your RPSMA to N type, we have a kit of 2 of them, and then we have end to end also, and all in different sizes here. And we also have end to end 12FX. So this is for our 11 gigahertz Ubiquiti parabolic antennas for the 11FX. And so this supports up to 12 gigahertz, but then these are just your typical LMR cables. But this provides that additional level of weather protection against, you know, rain and dust in order to kind of minimize your taping, either reduce it or remove it all entirely. But it definitely provides an additional level of protection that wasn't there before. And these aren't that much more expensive than normal cables. I think we only charge a few dollars more for them. This is a really cool product. We're excited that we partner with Cambium on. So this is an OMNI antenna that works for the Cambium EPMP 3K radio 3000. So this is released in stock now, and this works as a very low cost solution in order to provide you know, high throughput to you know, a small number of clients or moderate number of clients near the tower, all on one AP. So this provides you, you know, it's a little bit not confusing, but complicated, the construction on the inside, but it essentially provides this omnidirectional pattern here on all 4 ports, and then the radio is able to use its multi-user MIMO feature in order to get the high throughput. And so I'm just going to show here an example of field testing being done on one of the units. So this client here, he's trying to serve about 18 homes, but very expensive homes, so they have high data rates, and he just wants to use one antenna. So for his area, he had to paint everything camo because of strict architectural guidelines, and he was able to see you know, a substantial increase in his bandwidth from MU-MIMO during the evening prime time. Now with the shift to, you know, work from home, this is going to be going on all day, the multi-user MIMO, with these clients working from or end users working from home. So he's very happy with this antenna to date, and it's serving his needs well. So it's a way to reduce your infrastructure costs to get one of these radios out into your markets to serve high throughput customers. Now, at the same time, we kind of did a little oopsie. Sorry, I have to go back to this one. We did a part number change. So this used to be KP5Q SOMNI-13, but we changed to this part number. All of our websites almost being done updated for this, and we're sending out new documentation to reflect this to everyone. So the reason we did that is because we released this part number at the same time, and it's almost the identical antenna. The only difference is we actually ended up taking two normal OMNIs, 5 gig OMNIs, stacking them vertically in this radome, and then so this is just a typical OMNI, but instead of 2 ports, it's 4 ports, and this does not work with multi-user MIMO, so this is not the one to use with the EPMP3K, but this will work with any really 4x4 MIMO or 2x2 MIMO radios. So you could put 2 Ubiquitis on there, some Rockets, or whatever you want to put on there, and as long as you put them on different channels, you're going to be able to increase pretty much double your throughput, because you're at night with just one antenna. So you put 2 radios with 1 antenna, and this kind of minimizes the applications where, let's say you wanted to put up 2 OMNI antennas at 5 gigahertz. So now you just have to put up 1 OMNI antenna. We also have our dual band OMNIs, which are 4 ports, 2 ports for each band, 2 gig, 3 gig, 3 gig, 5 gig, 2 gig, 5 gig, to serve this very similar application. So here's our ProLine parabolic antennas. Just briefly, because I want to get over to some other cool things, is we released the 2 foot and 3 foot for the 11FX Ubiquiti radio, and these are available now. We have also released a version for the Mimosa, the B11. These are going to be in stock soon, I would say in the next month. We just had an issue with the virus situation, but everything now is kind of picking up pace and moving forward. So these Mimosa ones should be available relatively soon. Just kind of reach out to ISP and our sales team to kind of get the lead time on that. But these are high performance antennas, very easy to mount. It's the set and forget installation, inspired by the Radio Waves designs. And which has proven track record of decades of experience designing point-to-point antennas. So we're very excited about these ones. The 11FXs are doing very well, and the Mimosas we know are going to do very well too, and they're priced very competitively too. Just talking about ProLine stuff, so that's our ProLine 11 gig. We have our ProLine 5 gig dishes, which are wonderful. You might be wondering, why would I pay so much for a 1 foot and 2 foot dish and here's the prices here, when comparably I might be able to get a cheaper or maybe very equivalent antenna from another vendor. The reason is gain and patterns. These were designed to have very consistent gain and high gain across the entire bandwidth, and also the patterns were designed to meet very strict pattern requirements. We designed these for a customer that wanted to have a very dense application. Pretty much put a 2 foot or 1 foot dish on every home in a suburban or suburban/urban environment. So we ended up spending a long time reducing side lobes, improving the patterns as much as we can, and also still having high gain. So if you did a 1-to-1 comparison against this dish, 2 foot dish against some other 2 foot dish, I can almost guarantee you that you're going to see a higher throughput with our antenna. Maybe not higher throughput, but higher signal strength. So typically we see about a 1 to 2 dB increase in your receive and transmit signal strength when you go to the KP 2 foot dish. And that has to do with how we're actually speccing real gain and not directive gain. Now, we have those adapters I showed there for the C5C and also dual N-type connectors. We also just released this one for the Ubiquiti Prism Station 5AC, IsoStation 5AC, and IsoStation M5 radios. So this is just very simple, click and snap and put it on the back of the antenna, and these are available now. go next slide. We have a bunch of new OMNI antennas. We're kind of trying to expand our offerings a little bit more. So we have our 900 megahertz vertical pole OMNI antennas, and then also 2.4 and 5.8. And you'd be wondering why not dual pole? It's 'cause we already have dual pole. We just wanted to flesh out our lineup and get some more single polarization vertical. So these are great for little routers. Like the the Radiant routers or whatever it is, and then these are awesome for just utility markets where you don't have super high data rates, but you need a very dependable solution. And these are very robust antennas too. So we expect these to be used extensively in mission critical applications. Now, our ProLine sectors, just very quickly, we have a huge lineup of them, but I always like to focus on our small angle sectors. So these are great for your densification or where you want to get a very high signal strength in a small area. So very similar to a horn. In fact, they'd be almost equivalent to, if there was a 3 gig horn or 2 gig horn, they would be equivalent in terms of the azimuth patterns. So very good side lobe levels in front to back and high gain, 19 to 18.5 and 20.5 dBi gain for a 5 gig version. And they come in 2-port and 4-port flavors. This is just the patterns. I'm going to go over this, but here what I'm doing is I'm actually comparing one of our small angle sectors, the 3 gig 33 degree, versus a horn, a fictitious horn that works at 3.5 gigahertz and 45 degrees. Essentially, I took the patterns for a 5 gig horn and I plugged it down to these, or scaled it down to these frequencies. Now you can see here that the sector and the horn have almost overlapping patterns. So our small angle sector has almost overlapping patterns to the horn. Very similar. The sector does have a little bit higher side lobes here, but these are pretty inconsequential. Now, once you go and do your mapping on the ground, you can see here that very similar signal strengths in the forward direction, a little bit higher actually with the sector because it has a higher gain, and then slightly larger side lobes here, but it's nothing too significant. You can see these are fairly low values. So they essentially act just like a horn, these small angle sectors, and that's how you can deploy them in the field. So that's the kind of the thinking we'd like our customers to approach when they're picking a sector versus horn. It's not just on the antenna type. You actually have to look at the patterns, the gain, the beam widths, and make your decision from those qualities, as opposed to just focusing on grouping everything into one type of antennas. And then here's just a big line of the ProLine sector antennas. So what makes a ProLine? Just high level, very stable bandwidth across the entire band. It's got the lifting tow hook on it. We have the universal radio bracket on the mount. Very robust, like I would say over robust brackets on the back now. And very good front to back performance, VSWR port isolation performance. So we can see we have everything from 33 degrees, 65, 90 degrees, dual band, 4-port, 8-port, slant polarization. Now we released the H and V polarization 8-port, which is the one here on the bottom. And so these are great for getting lots of radios, lots of clients on one antenna to reduce your rental cost. Now, I'm going to segue into here. So KP is releasing ProLine horn antennas. And these horn antennas, we hope to be available at the end of July. Now, that's virus depending, but that's the date we have right now. So we're releasing 3 of them, base models right now, a 30-degree horn, a 45-degree, and a 60-degree horn. And we kind of design these looking at the market, what's available now, and trying to outperform the market in terms of the performance, and also being very competitive with our pricing. So these, some of the the selling features here. I kind of forget what slides I have here. Yeah, let's go to this slide. Ultra-wideband. And what I mean by that is, as these are the first horn antennas on the market that'll support down to 4.9 all the way to 6.4 gigahertz, and with such very good performance and side lobe performance across the band. So the VSWR is very low. This is actually a real data plot here, VSWR of both the ports, and then here's the port isolation. It's actually really decent. It's typically 30 dB, and then right at 6.4, which no one in the US is going to be using, hits 22, which is still very respectable. Some horns on the market are flat 20 across the whole band. So now what I wanted to kind of to emphasize here is the pattern performance. So what we did was spend a long time optimizing the patterns across this whole band, so it's very flat. And one way to kind of prove this, this is actually raw measured data of each of these horns, and there's actually multiple black curves on here for each of the frequencies, and you can see they essentially overlap. There's no huge outliers, no huge side lobe levels. All of these patterns are the same pretty much, like from 4.9 to 6.4 gigahertz. So you can be guaranteed that no matter where you are operating in the Uni 1 band, public safety, Uni 2, Uni 3, you're going to get the same performance characteristics, which is very nice to have that kind of assurance that's going to happen. The other kind of very neat features besides the electrical is the, let me just change this to turn off that. I got some movies here. Is the mechanical features. So we have, plus minus 25 degrees of azimuth and elevation tilt with markings on it to help you to kind of set the alignment. I'll be going over a few tips in order to kind of actually set alignment in the field, but this is going to help greatly to kind of make sure you set it right according to some propagation settings you did beforehand. The benefit here is we support mounting from 0.75 to 3.5 inch pipes, which is standard, but at the same time, you can actually do dual antenna mounting without having any special brackets. So this is how you would do a dual antenna mounting system for a 4x4 radio, or maybe just two 2x2 radios. But if you didn't want to do this, you would just use this back bracket right here. Now it has a quick connect feature, allows you to quickly snap in the radio, so or snap in the waveguide feed or the adapters, whatever you have on there. At the same time, allows you to adjust the polarization, which is a very neat feature. So now you're no longer stuck with H and V on the horn. You can do 45 slant. So that kind of opens you up to more different CPE radios if you didn't want to deal with the polarization mismatch. Let's say you just want to optimize it as much as you can. So that's this, and yeah, high strength radome on there. We are very conscious of radomes being broken in the field, so we spend a little bit of time to make sure the radome is high enough quality. And then these brackets are very robust aluminum, high strength aluminum cast parts. Now let's see if I can get to the next slide. There we go. So now with the release of the horn antennas, the 30, 60, and 45 degree horns, KP, I would say, has the antennas to do total tower deployments. So you can do your backhaul with our 2-foot dish, and then you can do point to multi-point with the sector antennas or the horn antennas to provide coverage close to the tower. The sector antenna to provide coverage far away from the tower. And I'm going to show a scenario where this is going to be used here. I'm just going to skip over this. This is essentially the different type of configurations you use in frequency planning, where each frequency would be a different color, let's say. So here's just one frequency with an OMNI, 360 degree coverage. But then let's say you wanted to upgrade to 3 sectors, 3 120 degrees, so they each have to be on their own channel, or 2 sectors back to back. You might be able to get away with this if they're spaced apart enough on the same channel. 90 degrees, you can do this all day long where you share just 2 channels back to back, AB, 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 or you could do three of them, but you're not going to be able to share channels here. But this would kind of be able to get you quasi 360 degree coverage, but you're going to have some gaps here on where they intersect. But yeah, I'm not going to go through the whole thing, so I want to spend a little bit more time on this. So we're going to talk about how do you upgrade for capacity. So let's say you're starting out in a town and you went and deploy 4 sectors, such as KP's dual band sector here. So I'm only showing here I think it's the 5 gig signal, but let's say you also have 3 gig on there to overlap, and you're providing some coverage maybe farther away with the 3 gig, and then 5 gig you're out here maybe 5-6 miles, probably a little bit farther. Kind of forget the scale of this, but you have 4 of these up, and then let's say, oh, now you think you want to start competing against some rural, the town's telecom, whoever's in that town providing internet to the house. And so you said, well, how am I going to do this? Well, I'm going to need high throughput. So I need to get as many APs as I can up, because they're going to require a lot of throughput. So what I'm going to do is first I'm going to deploy, some horn antennas. So you go look at your available spectrum. You say, oh, I'm using up the Uni 3 band with my sector, so I'm going to go down to Uni 1, so it can still have the 1 watts, and I'm going to put one sector here or one horn at 20 megahertz channel over at channel 36. Now you kind of expand upon this, and you put your next horn here at channel 40. Your next horn here, it's a little bit wider beam width, just because of how the density of the people there. So you go put a 44, or sorry, that's 60 degree. This might be 40 degree, but at channel 44, and you keep going here. Yeah, this is the 40 degree, and you put that at now you start reusing frequencies, because with the horns, because they have such low side lobe values, you can start reusing frequencies a little bit sooner. Instead of having to worry about going back to back, you can worry about just having enough angular spacing here between the two channels. So that's about I don't know, 90 degree spacing between the two, and that's sufficient. So you can start reusing frequency. So now you're just on 3 channels, 20 megahertz channels, and you're going all the way around the town. But you don't care about over here, because you got a sector giving everyone coverage, and you don't want to waste more money. So that's kind of how you do your deployment. And once you get the overall situation, this is what it looks like. So you have your horns overlapping with your sector. There's no interference with the sectors, because they're on totally different channels. Now, what happens if you want to upgrade your capacity a little bit more? Well, you can see here that we actually have room going from 20 to 40 megahertz. We can actually do that, so we can take up all the Uni 1 band, but then now for the Uni 2, you can see here that it's, or this channel, it's going into Uni 2. Now the downside here is that you're on reduced power, so you're at a quarter of the power, so you're not going to end up getting out as far. So you kind of try to align it so that this AP is either picking up clients close to the tower, or maybe you actually put a sector on there instead of a horn. I would actually kind of recommend against that, because the sectors are trying to reach as far out as they can, so they need as much power as possible. Where the horns, they have the benefit of having very good signal to noise ratio rejection. So they can have a very high center, even though they're low gain or low power. So I would say put the horn on this channel right here. Now we could go another step, if it was possible with the radio, to have 80 megahertz channels. Kind of the similar thing what we have here, but you got to avoid this weather radar block right here. But instead of putting the sector here in Uni 2, I would actually put the sector down here in Uni 1, and then just put the horns in Uni 2. Just because, like I said before, the signal to noise ratio is that much better on horns, because they can reduce noise level. So you're gonna probably be okay with a quarter of the power. It's all about the link budget. We approach it one way from having high gain, but the other side of it is having low noise floor. So horns do the low noise floor approach, but sectors have the high gain approach. Here's just another scenario using 6 sectors, 6 65 degree sectors. And then what you do here is a 3-channel approach. So it's ABC, ABC. And you're only using up these Uni 1 and Uni 2 channels. And this is kind of one way to do this type of deployment, and it allows you to maximize your channel size. So this is a very typical deployment we see with 6 65 degree sectors. And then going to 12 horns, it's actually, because of the narrow beam width of the horn, you actually don't need to take up that much more spectrum. You just need to take up another 40 megahertz chunk, because we can now do frequency reuse 4 on here. Even though we've doubled the amount of sector, we only need 1 more channel to achieve it, because now we're just trying to do ABCD, ABCD, ABCD. So how do you what's the important for maximizing your performance of your SM? Well, your SM, that's your client side, and your clients are the ones who are paying you. So if you have a higher performing antenna on the client side, typically what we see is that leads to a higher signal strength, and a higher signal strength usually means a higher data rate. So here, what we're showing here is that we're upgrading from a small integrated CPE all the way up to a 1-foot dish and a 2-foot dish. So here's the 1-foot dish. And we have whatever decent signal strength, and we're at lowish 25 or 50 megabits per second packages, and our revenue here is about 4,500. But once we upgrade to the 2-foot dish, yeah, you're going to pay an extra $50 per client, $50-$60, but you end up increasing your signal strength so much that you bump them up to their next modulation rate, and that increases their total max download and upload. And you can now charge them a little bit more for the next package if they want the next package. So this is assuming, of course, these clients want the next package, and who doesn't? If you give it to them, they're going to want it. And so now you can charge them a little bit more. And so now you're making $6,300 a month, $525 a month, $6,300 a year, just off these 6 clients. And that's going to allow you to recoup that extra CapEx investments very rapidly. So just from upgrading from the integrated CP with a 23 dBi going to a KP 2-foot dish 29 dBi, you're going to get your return on the investment just from these 6 clients in 2 months. And then everything else is gravy. And you're also going to have that very highly dependable solution moving forward. Same thing with your point-to-point microwave link. There's actually going to be, you're going to see a substantial difference between going from let's say an integrated CP all the way up to a KP 2-foot dish, all the way up to, I'm showing here Radio Wave's 3-foot and 4-foot dish as examples, but it's not just the increase of the gain. Yes, the gain is going to go from 23 to 35. That's going to be massive on your throughput. But at the same time, your side lobes are going to go down, your noise levels are going to go down, and you can see it here on the pattern mask. So going from a 2-foot to a 4-foot, if we have some radiation that's coming from this angle right here, unwanted interference, we're going to gain an additional, let's see here, that's about a 6 dB improvement, maybe 5 to 6 dB improvement, which is very substantial. That's almost 4 times the amount of noise level rejection going from a 2-foot to a 4-foot. Yeah, the investment's fairly big, but it's not that much to going from, let's say, the integrated panel to a 2-foot dish. So this is the cost with the 2-foot dish plus the connectorized antenna. This connectorized radio PTP 670. When you go to the 3-foot dish, it's a little bit bigger jump, but you can see here that in this environment that I went and did this all in Cambium's link planner software, we can increase our throughput from 143 to 330 to 409 megabits per second going to a 3-foot. Now going to the 4-foot antenna, it actually didn't have that substantial of improvement. And that's the reason I think that is, at least in the modeling software, is because we weren't able to account for noise coming from some certain direction. So if you have a case where you have noise coming in from a odd direction, you might see an actually bigger bump going from a 3-foot to a 4-foot. But for the most part, I recommend 3-foot antennas. It's all going to depend on on the distance of the link. This was only a 32-mile link, but upgrading from a 2 to 3-foot, it's not that much of an increase in your cost to do so. So now we're going to end this on the best practices. So we have a few minutes for this discussion. So when it's hard to give you a definitive answer of how far we should separate an antenna. We get this question so much. How far should I have 2 antennas separated between each other? It's all going to depend on a lot of different things. The antenna type, are they on the same frequencies? If you're on the same frequency, you got to have a lot of separation. 5 feet separation if you're doing back-to-back, or more if you can. Now, if they're not on the same frequency, so they're on different channels, you don't have to worry about interference that much between the two, as opposed to when on the same frequency. But you do have to worry about impacting the patterns of the antenna. So if I put a big metal sheet right beside the antenna, what it's going to do is it's going to impact the direction that the beam's pointing, and it's also going to put ripples in it. So what we recommend is, you have at least, 3, 4, at least 5 feet separation between 2 antennas that are side to side. Side to side you'll end up getting worse isolation between the 2 antennas, but they won't impact the patterns as much as opposed to up and down, stacking vertically on top of each other. So, side to side as much as you can, and 5 feet of separation. You got to stay out of these 2 zones, the reactive zone, and you'll most likely be in the near field zone, but try to be as far out of near the edge of it as you can. And these are 2 equations to calculate the near field radius right here, and then the far field radius right here. You can see this far field radius is going to get very big for low frequency and large size antennas. It also depends here on frequency. So we can see here that as the frequency increases, sorry, let's start here on the left side. As the frequency increases from yellow, 900 megahertz, to red, 5.8 gigahertz, that the near field zone decreases. So what does that mean? Sorry. Nope, it increases for an antenna of fixed size. So if you have, here we go, antenna of 2 feet size, the near field zone goes from 1 foot to 5 foot. So that means for a high frequency antenna, you have to end up putting it a little bit farther away to be out of the near field zone. Now, for free space path loss, you actually end up having to be, it's a little bit counterintuitive, but you end up getting higher loss at larger frequencies than lower. So it's kind of telling you that oh, there's a trade-off between spacing them far apart in order to be out of the near field zone, but at the same time you don't have to space it too much because the isolation actually ends up getting better at high frequency. So there's a number of competing things going on here, and there's not a definitive answer. So it's really a base by base case. Now, this is something a little bit more easier to give help on. It is really the best practices for alignment and installation. So one of the first things I can tell you guys is make sure you're using your link planning tools as much as you can. A lot of people will just try to wing it, which is totally fine. Just be expected that you might have to climb that tower maybe 2 or 3 times. Now, you know, I've used Cloud RF, Link Planner, Tower Coverage. There's a toll, which gets very expensive, but these are some tools that are relatively inexpensive to use. Link Planner is free, and it helps you get, what does it help you do? It gets your azimuth angles, your elevation angles, and your expected signal strength. And it'll actually tell you, you know, based off of the coordinates you put in, of your AP and CP, where to point this antenna with respect to azimuth and elevation. And also what's you know, it just helps you get in a better place so you're not blind when you're going up there. Now once you're on the tower, we recommend for your azimuth and pointing it, use GPS as much as you can and waypoints. So that means, you know, very good landmarks that you could use as reference, and then you can map out what the angles were based off of those waypoints. A lot of people use a gun scope. This is a gun scope here that someone retrofitted onto a bracket, and then they can put this on top of the antenna in order to help them align it a little bit better by eye. Now, for elevation, we strongly recommend you use a digital level, and you place it on the flattest surface you can. So on the parabolics, that'd be on the back of the N-type connector. You can also try to place it on the handle here if you're daring enough. The other, on the sector antennas, we recommend against the back of the sector, not the top. The reason is these top caps, you know, they're silicone down in place and then riveted, and sometimes this process can cause it to be slightly uneven, and it might be just a 0.2 degree, 0.3 degree, but we know that once you get at a certain angle, you can kind of get very large differences in signal strength on the ground by having a small, you know, half a degree misalignment in the elevation down tilt. So we strongly recommend use a digital level against the back of the sector antenna. And when you're doing these alignment, get directly behind the antenna, and just be kind of very careful and monitor the signal strength as you start rotating it. It's very, you know, much needed to have some guy being able to monitor the signal strength as you're rotating, because what can happen is you can think you have a good lock, and then you climb down the tower, and then you look at the signal strength and it's not where you expected it to be based off your propagation study. So then you go climb back up the tower and redo the whole thing again. When you're lining point-to-point dishes, one thing I've seen a lot is people will align on the side lobes. So always with a point-to-point dish, you have your first side lobe level, and depending on the antenna size, that could be 14 dB down, 10 dB down, 20, 25, 30. But they'll lock onto that side level and not the main beam. So that's why you have to be very careful that you sweep, you know, a large range of angles just to get a sense of the relative signal strength as you're rotating, and just make sure you find the maximum value. and not locking on these side lobes. So there are a number of tools on the market in order to help with this alignment. Sunsight, 3Z Telecom, SPAA005. These are fairly pricey. I wouldn't say that they're price prohibitive, but you have to make justify using them and make sure they get used in future installs before you go buy them. But there's definitely a lot of people are using these right now in the field. So just quickly kind of talking about radio combinations, just 2 more minutes. So with our dual band sectors, this one right here, it supports 3 gig and 5 gig, and we can support a number of different radios on both of these ports. So here's the different combinations here, using either anywhere from 1 Telrad at 3 gig to 2 BiCell 233s, or Nokia, or Ubiquiti Rocket. And then the same at 5 gig, you can put any radio you want on there. It's all about just matching up the number of ports. So this is an 8-port antenna, 4-port each band. So I'm going to need either 2 4-port antennas at 3 gig, 2 2-port antennas at 3 gig, 2 2-port antennas at 5 gig, or 1 4-port antenna at 3 gig and 1 4-port antenna at 5 gig. So it's all about matching up number of ports and the frequency, but now you have all these radios, either maximum of 4 or 2, minimum of 2 on just 1 sector antenna. And that's going to drastically increase your throughput. So if you're renting tower space, you're gonna really like this type of antenna, because you're gonna drastically reduce your tower space rental fees. So here with 2 gig and 3 gig, very similar. I'm not gonna go over every one, but just slowly, you can come back and look at the recorded view, or come in and reach out to us or ISP and kind of get an idea of what radio to use with this type of antenna. So here's the other 2 gig, 5 gig, 8-port radio, and the combinations that are possible. So that's it for me today. Jonathan, I think we're ready to open it up.
Great, awesome. Thank you very much for that detailed rundown, Justin. And we're really looking forward to all those new antenna and horn options that you showed us too. A few questions did arise. Here's a few of them. One of them is, can we use 2 Ubiquiti Rocket prisms on your 4-port 5 gig Pro sectors? If so, how much channel separation is needed?
Perfect. Yeah, that's a great question. So yes, you can. I don't know why it's not on. Oh, there it is. Here we go. We do the Prism 5 ACs, but it would be the same with the Rockets. Yes, you can. You can put them on. This is the 8-port version, but we have the the 4-port 5 gig sectors ProLine. You could put 2 Rockets on them. You're very correct, and they have to be on different channels. The channel spacing is really going to depend on the bleed off from the radios. So how tight are their channels on that radio, and the older Rockets, it's not as tight. So I would say as much spacing as you can. I would say probably 10 megahertz if that's possible, as a guard band between the two. But really, it's going to be trial and error, in order to make sure you get it right. But you're going to need some type of spacing, and it's always going to depend on that radio's filtering ability, out of band filtering, or out of channel filtering. So that's I'd say 10 megahertz, and it's definitely possible.
Thank you. Another question that came through is, are the nuts and bolts stainless steel on the horn antennas?
They are not, and we've heard about this complaint before where they're seizing. So these are not, wherever that is, these are going to be galvanized steel, or dacrylic coated, which is it's a different process than galvanization, but it provides the same amount of protection. A lot of our bolts are either dacrylic or galvanized coating, and we see very similar weatherproofing characteristics between the two. And they don't have the galling issue that stainless steel can have.
Awesome, that's good news. Now, a few questions here we did briefly cover, but just to recap, one of them is, when will your horn antennas be available, and what direct connect options will be available?
Sure. So we expect these to be ready in July, end of July timeframe. That's dependent on the virus situation. Luckily, it hasn't hit us too bad. We're considered an essential service because we do provide support for many different industries. But yeah, end of July, the adapters that are available will be the C5C, the IsoStation N-type. We also are going to do the EPMP 2000. That'll be the first one. The EPMP 1000, because you can use that with a 300 CSM. we're also doing the Ubiquiti 5X HD. That's the Prism 5AC radio, and also the Ubiquiti RM5AC light. So the newer M5 rockets, the lights versions of them. So those are the ones we're doing right now. We wanted to do the Rocket M5s, the old rockets, but it gets a little bit prohibitive to do them all at once. So this is kind of the way we staggered it out at this time. And Mike, I don't think I forgot one, did I?
No, not for the Ubiquiti. That was all of them.
Okay, perfect. Thank you.
Good deal. Thank you. And last question here is, will you be offering other licensed backhaul dishes? I have tried your airFiber FX 2-foot dishes and would like to see other options for Mimosa.
Yeah, so we're going to release the B11. You know, that one was supposed to be, I'm just going to go exit here and scroll up because it's a lot easier to do it. So we're going to release the 2-foot and 3-foot for the B11. This is the 2-foot probably right here. And you can see, yeah, that's the one. Yeah, definitely the 2-foot B11 dish. And they was supposed to be released at the same time. We just had some issues with on the production side that we had to resolve. These are actually on their way right now, and you can start placing pre-orders for them, but don't expect them to arrive. The 2-foots, sorry, I'm just going to open up this 2-foots. I think it's end of April would be the time frame to get the 2-foots. And then the 3-foots will be sometime May, probably middle or third week of May to have them in stock at our warehouses before we can ship out. So those are, at this point in time, these are the only license links we have planned, but we are evaluating doing other license links. As you know, Radio Waves is part of our team, and so all the license links that you want is also at the Radio Wave side too.
Fantastic. Thank you very much. And that wraps up the questions asked. If any other questions come up, please email them into us to sales@ispsupplies.com, and we'll make sure we get those answers for you. And if anyone is interested in going over pricing for any KP Performance antenna, please email us, sales@ispsupplies.com, or you can give us a call at 855-947-7776. As you know from today's webinar, they have antennas in every frequency from TV white space, 900 megahertz, 2.4, 3.65, 5 gig, and even licensed 11 gig. So they have a solution for you regardless of the need. We will also be posting a recording of this webinar on our YouTube channel as well as our Facebook page. So please make sure that you like and follow us. So I'd like to thank you all for your time today. Stay healthy, stay safe, and God bless you, everyone.
Thank you very much.
Thanks, John. Thank you, everyone.